Hi everyone. Our presenter today is Dr. Zhang connecting from Singapore. Thank you, Dr. Zhang, for joining us. So Dr. Zhang is a research scientist at National University of Singapore, and before his role as senior research scientist in Institute of High Performance Computing in Singapore, he received his PhD degree from the Nanyang Technological University in 2019. That's one.
Yeah, thanks for the introduction. So today, let's talk about how we can use the control theory for today's machine learning model. So basically, the title is how we use the control theory as a catalyst for modern machine learning. This is a joint talk with my collaborator, Chen Jingpu. So we are all from the Department of Mathematics of National University of Singapore. So today it's very common when you use machine learning for control. For example, the well-known paper, Lyapunov function. So we use a machine learning model to approximate the Lyapunov function and to do some control. And then similarly for robotics, we actually use a lot of machine learning technologies like reinforcement learning. We use that, for example, the actor-critic algorithms, so we can generate actions to the robotics. Okay, so these are very common in today's machine learning model. But what's more interesting is how can we use control for machine learning? So it's like the other side of this thing. So we try to use the control knowledge to help us to develop machine learning algorithms. So broadly speaking, we can utilize control for approximation analysis to optimize the neural networks, and more important, to architecture design of today's neural networks. And more specifically, we are going to focus on one area called efficient training in large models. Today's machine learning models becomes very, very large, and we actually need some specific techniques called efficient training methods to help us to optimize these large language models. So these are the 4 areas we are going to talk about in today's talk. So let me give a big background on why we can use a control for machine learning, or especially today's deep learning. The idea is many of the learning concepts have similar counterparts in the control aspect. For example, today we talk about the approximation, functional approximation, we're actually mapping an output of a data set. So this is very similar to the control knowledge we call the controllability. So the controllability is actually we try to control a few samples to their destination or their neighbors. So you can see these two concepts from learning and control, they are very similar to each other. Okay, so this is the one respect. The other techniques when we're trying to optimizing neural networks, or we call it the neural network training, it's very similar to the classical optimal control problems. So where we solve the optimal control problem with a PMP principle. Okay, there are other aspects like architecture design for today's neural network. It's very similar to the controller design in the classical control theory. So the good thing about linking these 2 areas is we have a lot of tools or existing results in the control theory. For example, the controllability theory, the PMP principle by Patriaghi, or the PID control, or even like an MPC. So we have a lot of tools from control, and we're curious how can we use these tools to today's machine learning problems. Now, one of the benefits of this aspect is machine learning model often tends to be a black box. We don't have enough theoretical understanding for that. But control theory has developed a lot of theoretical analysis for their problems. So in this way, we may want to use a control results to provide theoretical insights and help us to develop some new algorithms in the machine learning. Okay, so one of the most important architectures for today's talk is called a residual network. So basically, we have multiple layers where each layer is a residual block. You have the XT, and then you go through some neural architecture layer F, and you also have a shortcut to bypass this F. So in general, it becomes the residual form, or xt plus 1 equals xt plus some F function. So you can think F as one layer of a neural network or one block of a neural network. So the F can be like a fully collected neural networks as the FFN, or the convolutional neural networks, so the CNN, or even today's attention block like in what we do in the transformers. So this is the architecture we count on. Okay, so with this architecture, let's see this is the, let's see what, how can we formulate the supervised learning problems. Okay, so first of all, this is the standard supervised learning problems. So we have, our goal is to minimize some loss function J, and then we have some terminal loss L. When we compare the output of the neural networks with the true ground truth labels. So this is the loss function for the final state, and we have some regularizations on each layers. So it can be L2 regularization or other kind of regularizations. So these two things formulate the final loss for machine learning model. And then we start from the initial states, like xi0. So basically it can be an image or a sentence. And the dynamics is like we utilize the residual networks with some F functions. So this is a very standard supervised learning we try to in machine learning model. Okay, so when we compare this one to the classical optimal control problems, you can see they are very similar. For example, I showed the optimal control problems. You are also optimizing J with respect to some control variables UT, and you have some terminal loss with respect to the terminal states. So then you have some running loss. When you compare these two things, you can see this is a terminal loss from optimal control. This is a terminal loss we use for machine learning. And this is a running loss we use for optimal control. And this is the running loss we use for with machine learning. They are very similar to each other. And then the only difference is for optimal control, we often use the continuous case, whereas in the machine learning model, we often focus on the discrete cases. Okay, so the takeaway message from this page is they are very similar. But there are some differences we must be very careful. So first of all, the classical control theory is often applied on one or a very small number of objects. But where the control machine learning, actually we focus on a set of points instead of just one point. So we have a set of training data sets, and then our goal is to control these data sets to their corresponding target simultaneously. Okay, so this is what makes machine learning different from the control theory. Okay, the good thing is okay, the control system in the machine learning is rather artificial. Okay, so basically, so we can design the loss function, we can design the each block of this dynamics. So they are purely artificial. So we have the freedom to design a suitable system for different tasks. So that's the good thing we can do, and also different from the classical control theory. Okay, maybe my collaborator team will talk about something first.
Okay, thanks, Zhang. I will take a few minutes to give a very brief overview on some connections between the control and machine learning. Let's start with the approximation study in the deep learning. The approximation in the theoretical study of the deep learning, the approximation capability of a model simply refers to its capability to represent the target function with a high accuracy. This is a very fundamental aspect of the model capacity because it is independent of the training process and the data sampling. It is an inherent property of the model. By interpreting the deep neural networks as a control system, the approximation capability of deep neural networks can be formulated as a controllability problem over examples of points. For example, for a classification task, what we expect is that our deep neural networks can steer the initial state, the initial input features into several separable clusters where we can easily distinguish them. The ability of the model to realize such a control is called a controllability. And note that it is still different from the classical control theory, where we only need to control one or several objects. Here in the theoretical analysis of the approximation power, we need to consider the controllability over arbitrarily many or even infinite many points. So it is actually a very much higher requirement than the classical controllability problem. Fortunately, after some mathematical analysis, this problem can still be converted to a one single point controllability problem in a very high dimensional space. And classical control theory provides us very useful tools such as the Rashevsky theorem for the characterization of the controllability of nonlinear systems. And based on this viewpoint, the universal approximation property of various different residual architectures are established. This is a very fundamental guarantee of the performance of these practical models. Okay, let's turn to the next page. I'll briefly introduce some of the related works. In the first two papers, they give a very clear mathematical formulation of the viewpoint I just mentioned. That is, they formulate the approximation problem as a control problem, and they use the controllability tools to give the approximation analysis of affine invariant systems and neural networks with some specific activation functions, such as the sigmoid functions or something. And the third one and fourth one, they further demonstrate the related concepts on the controllability in regression problems and classification problems, and they generalize the previous results to much general kind of architectures, which is weakly depend on the activation function. And the last one further generalize these results to general activation functions of the deep neural networks, and even for much more general architectures such as transformers or something. All these works together provides a solid theoretical foundation on the study of deep residual architectures. Okay, now let's go to the second part. That is the control for the optimization algorithms in deep learning. Well, as we have mentioned, the learning problem can be formulated as an optimal control problem, and then optimize a neural network, or we say train a neural network. It can be regarded as solving the optimal control problem. And the algorithms for the optimal control problem is actually well defined. For example, the Pontryagin maximum principle provides a necessary condition for the optimal control. I think Dr. Zhang will talk about it in detail later, because it is related to today's work we will talk about. Here I talk it briefly. In the Pontryagin maximum principle, it consists of three parts. The first one is the forward equation, and the second one is a backward co-state equation. The first one it corresponds to the front propagation process in the deep neural networks, and the second one corresponds to the back propagation of the gradients. And the most interesting and the most important one, it is the third equation, that's equation 3. It shows that the optimal control for must satisfy the maximum maximal condition layer wise, and this condition is not depend is only depend on the zero order expression on the parameter theta. Unlike the first order optimality condition, where we require the derivatives of theta. Therefore, the PMP actually generalized the necessary condition for the optimality of the network in one way, that is, it does not require the derivatives of theta. So we can apply it to, for example, in the case where the derivative of theta cannot be get. For example, in the quantized network, where the weight of the for this paper, the first paper, where the weight of the network is discrete, so we cannot directly use the backpropagation and the gradient descent to train it. And on the other hand, it is shown that the PMP. Sorry, can you go to the last slide? Yeah.
This one.
Thank you. Yeah, it is shown that very naive numerical methods for PMP. That is, we solve this maximum condition with one first order gradient ascent. It is equivalent to the backpropagation in the which is commonly used in the network training. So this means that the PMP based the numerical based numerical methods for PMP actually generalize the backpropagation methods. That is, if we use other update methods for the maximization step, we probably get other novel training methods. Okay, now let's go to some of the related works. So the first one, they propose the discrete weight network and propose a PMP-based training algorithms. Since the maximization step does not require on the derivatives, so they can use to this discrete training, while backpropagation cannot be directly used to it. And the second one, the first one and the second one, they propose a very general framework on the training methods of the deep neural networks in a control perspective. And the third one is a good application of this perspective in the adversarial training. By using the PMP-based methods, this reduce the number of backpropagation significantly in the adversarial training process. And the last one is from the other aspect. They use the DDP-based, that is the differential dynamical programming. That is another numerical methods for optimal control. They use that method to develop a second order optimizer for the deep neural network training. Okay, now let's go to the third part, which is the most interesting part, that is called architecture design. Control theory, we believe that control theory can provide us very useful insights on designing a novel network architectures. In practice, there are a lot of factors we need to consider in designing a good neural network architecture. For example, its expressive capability, that is, it can it has enough power to representative power to express the target function, and the robustness, that is, it should not be sensitive to the perturbation on the input, and the parameter efficiency, that is, we do not want to introduce too much parameters or too much information to represent a target function. And control theory can contribute to these factors. For example, there are works where they want to enhance the robustness of the network. We are introducing the closed loop control between the layers of the neural network. There are two of them. For example, on the left-hand side, they at each layer they for trained neural network. Yeah, that is, they have trained. The black one is fixed, is frozen, and the blue one is the new introduced architecture. At each layer, they introduce very small blocks that to feedback the error at this the error of the dynamics at this layer to correct the mistake caused by the perturbation of the input. And the second one is applied to the transformer architecture, where they use the idea of the PID control. They introduce the PID term just like in the classical control theory, and that means they connect the current layer to the information from the previous layer. And both these works enhance the robustness of the networks in a very well. Also, by introducing these architectures, the expressive capability of the network is also is improved. That means the final accuracy of the training or test data is better. Okay, so let's go to the related works. So also the first one we just mentioned before, where they use a discrete weight neural networks. It can also be regarded as a control system design, which is more parameter efficient. That means since all the weights are only is binary, it is much efficient than the full precision weights. And the other two, they want to enhance the robustness. And I believe that the talks Dr. Zhang will talk about today, and that our work is also focusing on these topics. So let's give time to Dr. Zhang for the.
Thanks, Jingru. So I would like to add on a few points to that. So robustness is a very common concept in today's like a control theory, right? So we do see some works on applying this robustness analysis to today's machine learning model. So if you are interested, you can read these two papers. So the first paper is even more interesting. Like for today's machine learning model, when you train the model, you actually count on the gradient. So basically, you need to do gradient descent for the model. But in case like a discrete model, like a discrete way where you have only one or negative one or even zero, you have no gradients there because it's discrete. So in this case, optimal control does provide a solution for that. So in that way, we solve the optimization problem without any gradient. So this can be very novel. Okay, so the takeaway message from these three applications is like machine learning and control, they share very similar concepts in many aspects. So then we can actually apply this control knowledge to areas like approximation theory, optimization, or even architecture design. So these are the three areas we briefly discussed. But in the following minutes, I will focus on one specific area that we have been working recently. So it's called the efficient training for large models. So the motivation is very straightforward. So when we train like this weight model, for example, today's large models, the pre-trained weights can be very large. For example, in this case, it's a D times D block, a D times D matrix for transformer, and D can be like as large as 1,000. So the whole matrix can be pretty large. When you train this model directly or train the weights directly, it consumes a lot of energy and a lot of memory. The memory is a big issue when you train like today's machine model. If you want to train like a 7B or an 8B model, or NAMA or Mistral for example, these big models, then you have a out of memory issues. So the question we ask is like, how can we solve this issue when we training these large models? So the answer these authors provide is called a low-rank adaptation. So the idea is very straightforward. So you keep this pre-trained model W fixed. You do not train or touch it. The way you train is like you introduce two extra metrics, A and B. They are both low rank with rank R. And then because they are low rank, so it saves a lot of memory and computation resources. So in the tuition provided in this paper is like we want to approximate the weight changes of this W with some low rank matrices. So instead of get the training on W and get data W, we want to use the two low rank metrics to approximate that matrix. And the performance on that paper is surprisingly good. So let's say, for example, this RoBETA algorithm. RoBETA is a model that is a variant of BERT model. So BERT model is a very basic language model for today's machine learning. So if you full tuning the FT means full tune, you have tuned 125 million parameters. That's a lot of numbers, a lot of parameters. But when you try to use a LoRA, the low-rank adaptation, you actually only need to train 0.3 million parameters. You compare this value with the full tune, you see like we decrease the trainable parameters quite a lot. But in terms of performance on these data sets, you can see like for the first row and last row, we do not see a significant decrease for the performance. So that means like with a smaller number of parameters, we actually maintain the performance of the downstream task. So this is quite surprising and very promising for today's machine learning training. So in that way, we do not full tune the model. Instead, we use some simple blocks, and we only train these simple blocks after LoRA. But here's a problem. The problem is not from practice. In practice, we see a lot of successful stories. The problem comes from the theoretical understanding. So later we have a new variant of this LoRA. They call it adaptformer. The thing the piece of paper changes from the LoRA. On the left is a LoRA. You can see like they apply LoRA to the attention block only. They only apply the attention to the LoRA to the attention. And what adaptformer does is like shift the LoRA to be the parallel to the F11, which is a perceptron, is a feed-forward neural network. So the architecture design is very simple. You just shift the sequential model to the parallel model here. But the understanding to the original LoRA leads to big trouble. So for example, the F11 block is a nonlinear. And then we try to use some linear model, linear LoRA with A and B to approximate this nonlinear model, which tends to be very strange. Okay, this is paradox number one. The paradox number two is like if we want a full tuning, like we want to do a full tuning, then we need to train all these blocks, the F11, the near normalization, the attention, and the other near normalization. All these blocks we need to tune. But in this fine tuning with LoRA, they actually apply the LoRA to a specific block. For example, only to this block, instead of using to all these blocks. So that means like there is a paradox between the fine tuning and the full tuning. Okay, this is paradox 2. The more theorist part is the theoretical analysis. So when people develop the LoRA algorithms, they are following theoretical analysis on this research. But all this theoretical analysis requires a large rank. The rank can be pretty large. And then in the LoRA paper, we use a rank equals 1 or equals 4 for vision task. So this leads to a big gap between the theoretical aspects and the practical aspects. It's like theoretically we need a large rank, but in practice we need a small range. Okay, to answer the questions, like I actually plot the ranks we need to plot to approximate the data W. So I get this data W and do the SVD to SVD to get the true rank. It turns out the rank is pretty high. We need more than 500 ranks for certain layers. This is why in contrast, when we use A and B, we use a very small rank. So in other words, this data W and A and B, they are not exactly the same. Okay, so these are called the understanding issues of an adaptformer. But this is when the control comes and help. Okay, so I say that we rescue LoRA with a control aspect. Okay, so this is the adaptformer architecture. So if we relocate the LoRA module and we have an original block FT, which can be this F11 and LN. We have this block, and then we use some perturbation or some new functions GT. Then you can see like the dynamics of the models are changed from the original FT to the FT plus GT. So we can consider this GT as a control module. So as I plot in the here, it's a controller to the VIT block. You can see like this blue one is a pre-trained model. We keep it fixed, and we try and use some simple controller to perturb the VIT layer. So in that way, it is a control problem. Okay, so let's see what low-rank metrics are really doing here. To answer the questions like we need to recall the classical optimal control theory. So we need to introduce this Hamiltonian principle by defining some co-states P, as well as this original function and then the control function. This is a very standard way. And then with the PMP principle, Porto-Yakin maximum principle, we can use a similar way to define some PMP for this optimization. Okay, so to solve these PMP problems, they say like we need to do two extra regularization term. So for here we use last AT as well as the new AT. We try to maximize this Hamiltonian. This is the step, this is a very standard step in the PMP principle. Okay, so when we solve this problem, what we get is like these two equations. It looks a bit complex, but let me try to understand from the gradient descent. So what gradient descent does in LoRA is like we compute the loss function with respect to both A and B, and you can closed form solve these problems with this formula. You can see, okay, we are using gradient descent, and this gradient descent are almost identical to equation 9 and then equation 10. So in other words, when we use the gradient descent in LoRA, we are actually doing some optimal control to equation number 8. So in that word, so the conclusion for this work is like the optimization of low-rank matrix is not simulating the weight differences, but instead they are achieving the optimal controls on downstream tasks. So this is a different understanding from the classical machine learning community. So today, machine learning community can still consider like the non-rank metrics that are doing some simulation of the weight differences. But in fact, what we want to show in the paper is like they are achieving the optimal controls of the downstream task. So you can, for details, you can refer to our recent publication on ECCB here. Okay. Okay. All right. So the goal of this paper is more than just showing that. So we are trying to bridge the optimal control with today's LoRA training. So we have a special name for the LoRA training. We call it parameter efficient fine-tuning. So we try to reduce the trainable parameters in this fine-tuning process. So below I show the history of the optimal control. You can see like it all starts from 300 years ago when John Belloni first provides that variational method. And then we have a lot of great mathematicians working on these problems. From them, Leibniz to the maybe in the L'Hopital to Newton and then Hamilton and then to today's Porto-Yakin and his collaborators. We have a lot of history and a lot of tools for that. Right. All right. So in contrast, this is the history for parameter efficient fine-tuning. It's very short. You can see like arrow is very short. It's a start from 2021, and then we have developed a few tools, but our goal is to try to bridge these two concepts. So we try to say like we try to say like what we can learn from the optimal control and how can we utilize in today's parameter efficient fine-tuning or the PEFT. Right. Okay, so one of the case we can use, one of the case I propose here is called Bang control. Okay, so Bang control is a very classical algorithm in the optimal control theory. So the difference from the previous control is like we remove this regularization term. Okay, we only maximize the Hamiltonian. Okay, with this, we can actually solve the control in a closed form solution. You don't have to go into details of this closed form solution. The only thing that we care is like we only need the sign of the control. So basically, the control can take arbitrary value within -1 and 1, but the optimal control is actually the sign value of the internal value. That means we only take the extreme values of this control. Okay, so this leads to the controller design I plot on the right. Okay, you can see like in the previous we used some continuous function or continuous value for the control, but here we can use the binary control. We just use the negative C or plus T. C is some trainable value. So we modify the Bang control a bit. from -1 to +1 to this -c to +c. Okay, so we only use a binary control to the module. In that case, the controller becomes a binary control. We call it BIC. It's different from the LoRa control, but they do share some overlap. But they are all within the range of a linear controller. Okay, the very classical one, the linear controller. The benefits of such a binary control is like we can further reduce the bias from the algorithms. For example, from the adapformer, when we use a rank to 64, we have this. We can reduce the total bias to 1%, almost 1.5% of the original full tuning. But with a binary control, you can further reduce to 0.13% of the total bias. That is like a huge decrease from the original control module. And then in terms of the result, you can see like the performance does not decrease too much. Okay, so that's the big point for using binary control. But more interesting is like when we talk about the distributed optimization of federated learning in today's machine learning, we can utilize such a binary control. Okay, so the way we do it is we store the pre-trained models locally. Basically, the model is pretty large, and we do not want to transfer the model from one to other. So we just keep it locally on the computing nodes, and we only communicate the controller. Because the controller is binary, it's pretty simple. In that way, we can save the communication a lot. Below, I plot a figure like you compare the binary control with the adapformer. You can see like with a much smaller communication cost, you can reach the same test accuracy here. Okay, all right. So takeaway message for this work is like, okay, we need to provide a correct perspective for LoRa. Okay, they are not simulating the weight differences. Instead, we want to show like it's related to the optimal control, the very classical optimal control. And moreover, we can use some optimal control tools to develop the controllers for training large models. Okay, so this is work number 1. But so far, we have not answered another important questions. So we are going to discuss a bit on the second work. So the question is like, what is a theoretically good controller? So what principles should we obey to design this controller? So we call it controllability analysis for this work. Okay, to answer the questions, we actually need to define the very classical way. We call it local controllability. So let these values from the initial image to the features be the perturbed value input or the input-output map. Okay, so when we do the control, we actually want to perturb the output features in a small range or arbitrary in a small range. You can think like the original feature is deep in the space, and we want to perturb the feature a bit, but we cannot move it arbitrarily because it's a simple control. So we want to move to the neighborhood. Okay, so the definition, we define the definition for local controllability for machine learning is like we want the perturbed version of these data points to be an open neighborhood of this of our original features. In that way, we can provide a sufficient condition for control. Okay, so the idea is like because the perturbation of the features actually come from the perturbations of our control function. So the theorem is very straightforward. So we want the controller values to span the whole space. Okay, so for each layer, we want to control the values of this X to span the whole space, so it can go arbitrary way it wants. So this is the theorem we give in the paper in this year's ICML paper. And then based on this principle, we actually design some new controller instead for the LoRa. So here we can see like the control is still applied in parallel to the FFN layer, the feed-forward neural network. But instead, we use that LoRa base and try to add some nonlinear path. We call it the cross-patch attention, because the attention is a very important aspect in today's transformers. So we add this nonlinear model to this LoRa base, and you can see like the trainable values are still in the LoRa base, and we add the only thing we change is that to add some nonlinear paths which are non-trainable. So we do not introduce any other parameters, but instead we just from linear control to nonlinear control. Okay, so with that case, we can see like on the right is the LoRA, because it's a low rank. So after certain ranks, at certain ranks, you see like we cannot go the singular values go to 0. Okay, so that means that your value cannot go, the perturb inputs cannot go into these directions. And then, but for us, we can like perturb in this way. So these values can still go in these directions. So in the other words, the singular values span all the whole space. So this is the new controller design. Well, of course, this is a very new area, so we are still working on it to make the controller more effective. But okay, I think that's all for our talk. Let's see if we have any questions on that.
Questions? Okay, I do have one. This is a very silly question. I guess I'm not very familiar with how the communication cost was evaluated in the previous when you talk about binary control method. Yeah.
Okay, so just count how many ways we need to transfer from each one to the maybe the central server.
Oh, I see. Okay, that's easy. In the previous slides, is that a similar way to evaluate the total bytes consumed? Is that the same evaluation?
Yes, correct.
I see. Thank you.
Yes. Thank you for your talk. Have you thought of incorporating in the controller strategy the length and the width of your network? Let's say the T capital and the number of neurons at each layer at the same time. So find a controller between the layers, but at the same time find some guarantees of the how large T capital is and the width of your network.
Can you repeat your question? I cannot hear you. Can you?
So if in the control strategy, maybe I should.
Yes.
If you have thought about, I think there are some works about the length and the width of the network, and taking into account that this is variable and you can somehow play with these parameters, is a control strategy related to finding a strategy that changes width and length of your network?
Okay, so a quick answer is that we do not consider the width or the length of that layer, but it can be very interesting. Like your controller should be related to the width of the layer, right? This can be a promising area.
Oh, yeah, thanks. Nice.
Do you have another question? Do you have any questions online? No. In that case, thanks so much.
Yeah, thanks.